Now let's look at the first example problem for minimum spanning tree. So this is a problem from Cont'd. It's called a feast for cats. So here's the problem description. So given a certain amount of milk and C cats, and these cats, they are sitting in a way so that every pair of them have a certain amount of distance from each other. And your goal is to feed every cat at least 1 millimeter of milk. And while you're carrying milk around, you will also spill them. So you will spill 1 millimeter of the milk for every meter you travel. So, however, instead of carrying all the milk at once, you can choose to put some amount of milk down where a cat is, and then you can only carry some portion of milk to feed other cats, and then when you come back to this place, you can pick those up, and then then carry it to other cats. So essentially, what this allows you is you don't have to spill milk both go to the cat and then also spill when you come back. Suppose your goal to go a particular way is only to feed that cat. You only need to carry 1 plus the amount you have to spill. After you're feeding that cat, when you come back, you're actually empty-handed. You're not spilling anything. So yeah, so the cat will not drink the excess milk you left there, and the fridge is placed at the same location at cat 0. So essentially, we can forget about the fridge and just think about the cats. So we have up to 2,000 cats, and the number of milk is m, and we also have the distance between every pair of cats is in this range. So the problem also says that the cats coexist in dimension far greater than 3. So it essentially, because they give this arbitrary pair of distance, it's quite possible that for a lot of the data set, you actually can't place the cat in a way so that their pair of distance exactly come out to be that. So that's sort of I guess the guy who gave the problem, they sort of know mathematics well, so they just give that as a caveat. So basically, you just think about graph. So forget about the cats. It's essentially just a graph. We have edges. In fact, this is to be fully connected edges. So complete graph, and each edge has a weight, and we're trying to figure out how to feed the cats. So I encourage you to pause the video, think a little bit how to solve this. You can also go to Cont'd site to look at the full description, to think about it before coming back. So it may not be obvious, but essentially, this question asks for a minimum spanning tree. So we talk about the concept of minimum spanning tree. So it may not be obvious why the minimum spanning tree, in fact, the total cost of minimum spanning tree plus 1 for each cat is all you need. So this is because we can take advantage of leaving the milk at the node and pick it up later. So for example, assume that this point is where we have the milk. This is cat 0. And these black lines, these bold black lines indicate the minimum spanning tree. Then because of that, then we can leave the milk here. We can try to serve this cat first. We just need to carry 6 milliounce. So we'll spill 5, and then we have 1 left for this cat. And then we come back, and then we take all the remaining milk down here. So we will spill 8 of them. And then at this point, we have 3 more branches to travel. Here, here, and here, here. So we can determine how much we need for each branch. So for example, for this branch, what we need is 9. So then we just carry 9 unit here, so we'll spill 8 and have 1 left for this cat. And then we come back, and then we can carry 5 here, so spilled 4, and then give this cat 1, and then we come back. And then we take the rest of them. So in fact, we need 11 plus 6, that's 17. We need 19 of them. So we can carry 19 of them to here. We spill 11, we give this cat 1. We carry the rest of them, 7 to here. We spill 6, and we give this cat 1. So essentially, the total amount of milk we have consumed is 1 for each cat, plus the minimum spending tree cost. So to determine whether the amount of milk is enough, we simply need to compute the cost of the minimum spending tree. So here is implementation using Kruskal's algorithm, which is really short and nice because sort of the key part are in the unified data structure, which we shown on an earlier slide. So here we store the information in an edge array. So each edge is represented using 3 values. So the weight, and the 2 nodes, so weight and U and V. So I put weight first, and because then we can sort it. Oh, and this use my sort of a favorite comparator, which will compare interarrays in sort of essentially first compute the first element. If that's equal, we compute the second, and so on. So that will determine this sort is primarily based on weight. So then we create a unified object node, and initialize minimum cost to be 0, and k is the number of nodes. No, actually k is the index into the edges. So we'll just increment that every time with the loop, and we will stop when the number of sets in the unified data structure is exactly 1. So that means everything is fully connected. So this node.count include the number of different disjoint subsets in the unified data structure. So yeah, so that's the loop condition, and each time we'll just access the case edge. So we get the 2 nodes, and then we check whether they are already connected. If they are not, then we will add this edge weight to the minimum cost, minimum spending tree cost, and then we will union these 2 nodes. So that's all. So because after this, it's really just the minimum cost plus number of nodes, whether compare that with the initial amount of milk we have. So that's it.